All right, thanks, Arbin, and thanks to the organizers for the invitation to speak with you. And Dave and Arbin asked me to speak on this topic. I'm looking forward also to the other presentations in this session. Verification and validation as a topic has come up a lot the last 2 days, so it's good to hear. I'll probably fly through some of the stuff as background. This might be a bit of a hodgepodge of talks. And let's see, I'm not able to advance my screen. There we go. So I want to acknowledge my coworkers, in particular, Anders Peterson and Bjorn Sjogren, who I've worked with for quite a long time. We started with institutional funding that actually Dave helped us get. Dave McCallan helped us get back when he was a Livermore employee. Lately, we've made a lot of effort to advance the capability thanks to the exascale computing project that Dave talked about yesterday. And a number of folks have contributed to this effort, particularly collaboration with engineers who have provided valuable feedback for how to improve the capability. And none of this work would be possible without the computing facilities that we take advantage of and we're able to run our calculations on. All right, so 3D wave propagation simulations are complex. They require validation and verification. Ground motions, as we know, depend on many factors, and simulations have to get all of these correct. Verification and validation is crucial for demonstrating accuracy and building confidence in solutions. They're key to accepting simulated ground motions in engineering applications. And the numerical method must be accurate, and the computer code must solve the algorithm correctly. And this is the realm of verification, code verification. And the inputs must be accurate and physically meaningful. And that includes the source, which in this case is the earthquake rupture, and the three-dimensional earth structure must be accurate. It must include all the fine details of basins and crustal structure, topographic structure, and also site effects. And this is the area of validating the capability. Related to this is performance benchmarking, which is important in our project, trying to make simulations easier to do so we can have a greater throughput to look at many realizations of the Earth model or the rupture model or different events. All right, so SW4 is a summation by parts finite difference code. It now includes a curvilinear mesh refinement capability. So we can refine the mesh in this upper topography conforming part of the mesh. It's fourth order in space and time. It's been hosted at the, it's open source and available at the CIG GitHub site. And in recent years, optimizing the code to run on specific hardwares has been a big part of the effort. And adding algorithmic improvements to make these calculations be essentially less expensive, be easier to do in shorter time. Our demonstration problem, Dave talked about this in yesterday's the late session yesterday. It's a magnitude 7 simulation on the Hayward Fault here in the San Francisco Bay Area. We've been focusing on trying to increase the frequency resolution, trying to get to 10 hertz so that we have a fully broadband and deterministic simulation. This requires very fine discretization of 6 1/4 or 3 1/8 meter, at the surface. We're resolving wavelengths as small as 50 to 25 meters and looking at low shear wave speeds at the surface, first at 500 meters per second, but more recently 250. And we use the USGS 3D model, which goes back to 2005. And Evan talked about this yesterday a bit, and we use the Graves and Petrarca rupture models in our simulations. So this is a slide from Dave, and as part of this exascale computing project, we have to determine a figure of merit, which is a metric of computational efficiency, normalized to 1 for when we started. And we've been able to achieve really significant speed up of or increase in this figure of merit, which depends on the maximum resolve frequency, the wall time needed to perform the calculation and the minimum shear wave speed. Lately, we've been doing this with 500 meters per second. We're dropping this down to 250 now. All right, so verification is a mathematical and computational evaluation of the solutions to check their accuracy. And a comparison can be made of computed solutions against analytic solutions or other computed solutions. And the goal is to obtain accurate, reliable simulations of the seismic response to build confidence in the solutions. There are several criteria that people have used: point-wise differences between solutions, goodness of fit measures on waveform derived measurements, or time frequency phase envelope misfits have been used using wavelet decomposition. And there are a few notable examples. This peer study from 2003 defined a number of canonical tests that are now used by our group and by many groups. Many people, we've heard from some of these folks this week, are key contributors to this enterprise. And some also, Manu Chajoub talked about some stringent methods for comparing synthetics, and that's highlighted and hit the paper that's cited there. We'll probably hear from Ricardo on some of these as well a little bit later. SW4 has an option to use something called the method of manufactured solutions for testing accuracy and convergence. We know the wave equation. Rather than specifying the forcing and the Earth model and solving for the response, one can choose the response, plug it into these equations, and these are simple harmonic functions. One can analytically get the response in a also chosen harmonic 3D Earth model. And this is written into SW4 for checking accuracy and looking at the convergence by running the code with different grid spacings. One can numerically measure the convergence, and it's called twilight mode. It's one of the features that's built into the code. But this can be done, with routine builds and as part of the acceptance testing for new builds of the code. When we recently, a big part of performance improvement has been porting SW4 to be able to run on heterogeneous GPU, CPU systems, because this is where high performance computing is going to add GPU acceleration. And this uses something called Raja, which is a way to generalize how work is offloaded to the GPU parts of the computer. It has the advantage of not making major changes to the source code. So what we did when that came online is run two calculations, magnitude 7 on the Hayward fault, resolve 0 to 5 hertz, and compare the CPU, pure CPU calculation on Cori, shown in red, and the GPU version run on Lassen at Livermore, and for 2,300 sites spaced 2 kilometers across the domain. We did point-wise comparison, and we got agreement to single precision, which is how we're saving the response. So that's an example of just having confidence that now the port from CPU to GPU heterogeneous machines gives us the right answer. More recently, we've been focusing on this curvilinear mesh refinement. So in the past, we would have a curvilinear mesh in the top parts of the model, and then refinement of the regular Cartesian domain. Now the Cartesian mesh can be refined closer to the surface, which means as the wave speeds increase with depth, we can have the grid get coarser. When we do that, we get, for this sort of Hayward fault long and skinny domain here, shown in the upper right, we get a reduction of about a factor of 3 of the number of points that are required. And this can run on the same resource less than half the time. So it's a great efficiency speed up, and similarly, we're getting good point-wise comparison. So in these problems and in these projects where we have ongoing continuous development, it's important to keep verifying. All right, well, model validation is a little bit harder animal, I think. We've seen great improvement in the ability to calculate seismograms. And we've seen that just in our project, but also just in recent years. But there's not a commensurate improvement in the 3D Earth models. Just because we run a 1 billion point simulation doesn't mean we know 1 billion unique things about the Earth. So this is actually harder, and particularly the Earth model validation. But what validation is comparison of computed solutions against empirical data. And this tests the inputs. In particular, for this type of problem, it's the source or the earthquake rupture model and the Earth model, usually 3D. And this should really only be done with a code that's already been verified. And the goal is to ensure that simulations predict, simulation predictions or waveform simulations are realistic and consistent with empirical observations. And this also is to build confidence. Using moderate earthquakes, these are of great value for testing wave propagation in the 3-dimensional Earth. And there are a number of examples in California cited here. Large scenario events without empirical data are tough. We didn't have any seismometers in 1868 to record the last major Hayward fault rupture. So we're either left to compare against ground motion models or so-called GMPEs, or look at data from similar events. And Floriana this morning talked about that specifically with some of the simulations that Arvin and I have done for the Hayward fault. So to go back in time, though, an earlier validation study looked at these 12 events in the Bay Area recorded at broadband stations. And we see lots of good agreement with long period response, but we see biases where these waveforms have to be shifted, in some cases by a few seconds, which is a fraction of a wavelength at these long periods. And we capture some of the late arriving features in the data. But looking at, say, this Bolinas event out here, we see overall fair agreement, but you can see almost every seismogram requires shifting. And because of the multi-scale nature of linear wave propagation, these small shifts at relatively long periods are going to translate to big effects at short periods, and we're not going to be able to match wiggle for wiggle. But it's this kind of data that's going to be key for 3-dimensional full waveform tomography or adjoint waveform tomography, which I think is going to be an important methodology for improving 3D Earth models for waveform simulation. More recently, I've looked at these 8 events in a similar domain, but adding the strong motion data, which greatly improves the path coverage, as you can see here. And for this Gilroy event up to a station in Briones in the East Bay, we see the red being the synthetic is higher amplitude than the blue, the data. We're matching the duration pretty well with this 3D model, including topography. But in the ratio of the Fourier amplitudes here, we see the simulation provides too strong an amplitude. Similar path from Gilroy, or a path from Gilroy to Stanford over here does better, but it maybe underpredicts a little bit in this mid-period range. These are simulations that are valid to 1 Hertz. We've seen in our simulations of Hayward fault earthquakes very large amplitudes in East Bay Hills. Evan talked about this yesterday. I'm hopeful that the changes that Evan and Brad Agard have made to the USGS model will correct some of these biases, and we're eagerly awaiting to see that model. Okay, on to our demonstration calculation. This magnitude 7. Now, as we go to higher frequency, we expose potential shortcomings of the source model of our assumed minimum shear wave speed, which then impacts the geotechnical response, and just the fact that we're using linear wave propagation and not able to model nonlinear effects. We've published a number of papers on this, increasing the frequency content, and this shows an example of looking at, from an earlier study that was valid 0 to 4 Hertz, comparing PGV with the ASK 2014 NGA West 2 model. For a 1-dimensional flat Earth model, a 3-dimensional model with no topography, a flat free surface, and the 3-dimensional model with surface topography. The PGV values look good. We see a separation of the east and west sides, though, and relatively unbiased for PGV. from looking at spectral accelerations from 5 hertz or 0.2 seconds to 10-second periods. We see across this band, you know, the median values are close to 0 for all of the cases. And we see an increase in the variance as we go from 1D to 3D flat to 3D topography. But unfortunately, I mean, all of these cases have less variation than the within event variation that's seen in the ground motion model. So that remains a challenge to remedy. As we increase frequencies across the band, looking at epsilon values, you know, the red shows a simulation that's valid to 1.25 hertz, the yellow for 2.5, the green for 5 hertz, and there are 3 simulations at 10 hertz. We see that we bring the epsilon values in line with 0, indicating that on average, median, the simulations are unbiased, but that doesn't necessarily mean that they're true. And they, in fact, we looking at PGV across the domain, we see very good agreement with, in this case, this is ASK. But if we look at PGA, we have very large accelerations near at short distance. In fact, extremely high, right? 2 or 3G. And it's not surprising though, because these are areas that have low VS30. And we're running a linear elastic code that does not include the dampening effects or nonlinear side effects. So there are competing effects, right? Our assumption of the 500 meters per second means we're going to get a lower motion than we would expect in the real world. But if we're subjecting that site to 1G or 0.6G acceleration, we expect there to be some nonlinear damping. It's possible to develop site corrections. And when we do that, we can bring the observed, this is for a site here in Berkeley, we can bring that site in line. I wanna, my time's running out, so I wanna jump to the conclusions here. But I just wanted to, you know, to highlight this, that side effects are something we're thinking about. And there's a, you know, and as we've heard this last 2 days, it's an important topic that deserves a lot more attention. So verification is an essential and ongoing task for seismic simulation codes that are undergoing continuous development. And validation is needed for both the source and the 3D Earth models that go into these simulations. In particular, validation of path propagation effects in 3D Earth models with moderate events is very important. And we must learn as much as we can from small events. Small events are much more important than maybe they have been in the past. And this includes basin effects and crustal structure. And we're waiting, like I said, to look at the update of the USGS model. Validation of large event scenario ruptures is more complex because of the lack of empirical data and the dependence of the intensities on, you know, region-specific geometry, source, path, and site effects. Simulated data may be consistent with the GMMs, like in terms of median motion, but that doesn't mean that the Earth model is correct. And looking at additional criteria, some of this has been talked about already. You know, we've focused on first looking at median epsilon values, but looking at the variability, spectral correlation, as Jeff Bayless talked about today, is important. Duration and building response and engineering demand is important as well. So one last, I think this effort kind of is consistent with some other things I've been thinking about also, and would like to sort of propose some recommendations for community-based verification and validation. Following fair best practices, findable, accessible, interoperable, reusable best practices. This is important movement in science to make work more usable and extendable. And this could involve, say, version control on data sets, synthetics, and 3D models. We should standardize the event and parameter data that are used in validation studies, and perhaps assemble these data in Python using OBSPy and Jupyter Notebooks, store the data in ASDF, which is a single HDF5 object per event, which simplifies transfer and contains all the data and metadata. We could standardize how simulations are performed, and also consider the metrics so that they could be processed together. And I'll stop there. Thank you.
Okay, Thank you, Artie, for this very interesting